This is on Zinc, minimal kernel crypto API, which is really trying to be a non-API. We're trying to be the most boring possible way of adding crypto to the kernel, which is just C function calls. So let's dive into things a bit. So some background, I'm Jason. Usually I break stuff. Last couple of years I've been making WireGuard, bit of a change. WireGuard has some strange design goals for the kernel. Trying to be really short, trying to be implementable with basic data structures. The design of WireGuard is meant so that you can implement it with really kind of simple code constructs, and that the best coding practices come naturally from the requirements of the protocol. There's minimal state that's kept, and we don't do any dynamic memory allocation in the fast path for packets. And we want a stealthy and minimal attack surface. So the big question with this is, can these objectives be accomplished with the current crypto API? The answer I've found over and over is no. In the course of writing WireGuard, I wrote it with the crypto API in the kernel, and then I saw that it was horrendous, and I switched to using some just kind of basic functions, and I thought, well, at some point I'll get rid of those and switch back to the kernel crypto API when I can actually figure out how to use it in a way that's not terrible. And sometime later I tried again, and I wasn't happy with the result. It bloated things, it made things unusable. And we went kind of back and forth, I don't know, 6, 7 times of just trying to use the crypto API in a way that looks sane, and it couldn't be done. And so it seemed like a good opportunity to actually go full on ahead with making a minimal replacement. So let's do a little case study. Not of WireGuard, but of something even smaller, which is this thing called Bigkey. It's a key type for the kernel's key retention system, where usually you can give keys to the kernel and it'll keep it in memory and only give access to it if you have certain permissions. But what if you want to give a really big key? And so there's some crazy scheme where it will encrypt your key with another key. It'll keep that key in memory, and it'll write the encrypted ciphertext on disk. So then if you have a megabyte key or something, you won't have to store that in unswappable memory in the kernel. You can put it on the disk and just have that encrypted so that someone with access to the disk can't get access to your key. I don't really know who uses this or why, PQRSA or something, I don't know, but it's there. So I took a look at this a while ago, and the crypto was totally broken. It used ECB mode, which if you look at the picture, there's the Linux penguin, and when you encrypt it with ECB mode, it encrypts it, but then you can see it's still a penguin. It was missing an authentication tag, so you could modify the ciphertext to influence the plain text, and it would not be detectable. It didn't really use a good source of randomness in the correct way. It was reusing the same key over and over, which led to some catastrophes. It didn't zero the keys out of memory. There was a lot of CVEs from this. And so I thought, well, all right, I'll just rewrite this using the kernel crypto API in the proper way, and maybe experience doing that will transfer to WireGuard, and I'll be able to then finally use the crypto API in the proper way in WireGuard. So I went to do that. So the first thing we have to do with the old crypto API is you have to allocate an instance of this cipher object that is then going to give you access to the underlying algorithms. And you pass it there, this crazy string. We want AES GCM, but they've got their own domain-specific language for specifying arbitrary complex constructions of ciphers, which is crazy. You pass in async to indicate to this API that you don't want it to be async, because it's actually a mask. This is terrible. Then you have to set the authentication tag because they're size, because there's variable length sizes for these. So this is done at mod init time or something. We also need a mutex, which we'll see later. So then when we actually want to encrypt something, we have to allocate more memory. So now we have to allocate the request structure. And then we have like all these complicated calls. We have to use scatter gather to even pass data to it. We can't just pass it an address. And because we're using scatter gather, that means we can't use things like Vmap addresses. We can't use addresses off the stack. Those are things that you just can't encrypt with the current kernel API. So we make a scatter gather array, we init it, we tell it that's what we're going to crypt or something. We give it a callback function and indicate that this could sleep because it's all asynchronous, except we don't actually want to give it a callback function because we specified the async mask in the beginning, so we just pass it null. We give it the length of the additional data. If that had a positive length, I think we'd shove the additional data in as part of the data to be encrypted, even though that's not encrypted. This is nuts. Okay, then we actually want to set the key to be used, except the key that's used for the kernel crypto API is attached not to the request object that we just allocated, but to the global instance of that algorithm that we allocated at mod init time. So if we want to set the key, we have to take a mutex, we got to lock. Otherwise, if another thread is trying to use the same object at the same time, then it'll change the key of our one object. So that means if you want to encrypt multiple things with different keys, you either have to allocate tons of objects or use locks. Yuck. I mean, if you remember with the WireGuard requirements, we don't want any allocations. I mean, so what would the options be? Like having a pool of these to choose from that are pre-allocated and like managing that. Now these are not, now I have to have a whole file just handling pools of these objects. But what if it's not in heavy use and I don't want that many objects pre-allocated? Am I going to like reinvent a Malloc? It sounds like dynamic memory allocation all of a sudden, right? So that's what it looks like after rewriting it. But then Bigkey likes to Malloc sometimes around a megabyte worth of material. Turns out that on some platforms you just can't Malloc that much. And so the solution usually is kvmalloc, where you try and kmalloc it, and if it fails, it falls back to vmalloc. It's a usual pattern used everywhere. If it's too big, you use kvalloc. But no, you can't do that with the crypto API because you can't encrypt vmalloced memory. So there's this commit from Dave Howls earlier this year where he realized this, but rather than use vmalloc as one would hope, he implements his own crazy vmapped allocator situation. So that looks kind of like this. First, he allocates like the structures that are going to keep track of all these different pages. And then he makes a table, and then he allocates a page for each one and like does all the complicated pointer arithmetic. And then he vmaps all of these and finally can return that. So all right, that's fine. That's a good competent code. It looks nice. It follows conventions. But like really, we're in Bigkey, which is like some a tiny little thing, and all of this just to encrypt a buffer. This seems a little bit ridiculous. So I mean, just to recap on what's required here is we've got to allocate once per encryption. You have to allocate once per key or take mutexes. You can't use stack addresses, can't use vmalloc addresses. You have this bizarre string parsing situation, even choose which algorithm you're going to have. The whole thing is this enterprise API. I mean, it's definitely been developed by some smart people who can really code in crazy ways, who can, really push the limits of what we're used to in C. It's impressive, but this is a big, fancy enterprise API that is not appealing to me to use. And importantly, it's hard to use, which means when people try and use it, oftentimes they get it wrong and there are bugs. With something like crypto, where people are already making the bad choices on just what crypto to use, you don't also want to have a hard interface that's, now they're making problems with choosing which crypto and how to use it as a disaster. So when we replace this in Bigkeys with Zinc, we removed 200 lines and we added 28 that essentially amount to this. We allocate the buffer. Bigkeys wants a new random key each time, and it's going to store that past the stack. So we allocate a place for the encryption key. We choose the random bytes, and then the Zinc part is just that last line where we call encrypt, and we pass it the buffer and how big it is, and then it does it. And that's it. It's a series of functions. So this is not a crazy API. I mean, the innovation here is realizing that C has this thing called functions, and we can write them and use them, and then everything goes well. We're also trying to do a good job in the implementation. So we're going for high speed and high assurance implementations. And we want to keep this, for now anyway, as software-based things, so things that run on your CPU. We're not trying to build a crazy async architecture that, that involves sending things to some other device and then getting a callback sometime later. We're just trying to keep these as like the simple software core. So what we have for now are things that WireGuard uses to start out with. So we've got Cha-Cha-20, which is a high security stream cipher, Poly 1305 for authentication tags, and then there's this construction of the two of them that makes it into what's called an AEAD, authenticated encryption with additional data. There's like an RFC for it, it's in TLS, lots of things use it, WireGuard uses it. We have the Blake2S hash function and PRF, which is kind of super fast on all hardware, and it's like as fast as MD5, but it's as secure as SHA-2. Kind of nice trade-offs in all directions. We have an elliptic curve Diffie-Hellman function, so a real-world example, we saw the one with encrypting a buffer. For hashing, the APIs are kind of similar to what you've seen before in other crypto libraries, very familiar. You can hash things all in one shot, and you just give it all of them, or if you're kind of constantly sending in more data to be hashed, then you use the Blake2S update function, so you have init that establishes state, and you call update a bunch of times, and then final when you want the hash out of it. This might be new to some of you in the room, but if you've ever used a crypto library before, then this should be a super familiar pattern. The innovation here is that now you can do in kernel space. Again, this is not like super innovative here. This is mostly the slog work of kind of ripping out all the enterprise stuff and replacing it with things that C programmers are used to using. You can just call the function directly. Like this auth encrypt HMAC junk this is a string I took out of the kernel. Like this is how these are currently being described. I mean, this arbitrary. I don't know. It's nuts. But people might want dynamic dispatch. I mean, I don't really like Cypher agility, but other people do, and there are kind of existing systems that do have that, like dmcrypt and IPsec. You have plenty of good quasi-legitimate use cases for that. And so you could implement dynamic dispatch on top of Zinc, like depending on what the descriptor is, then you call out to one of these functions. Actually, we've already started refactoring parts of the existing crypto API. It keeps doing its enterprise stuff, but instead of implementing the functions itself, it just calls the Zinc function, which I think makes what the crypto API is about more straightforward, because then it can just focus on being its enterprise API, while Zinc will focus on having the really kind of streamlined small implementations of that. Tons of crypto code has already been kind of gradually snuck into the lib directory. There's like SHA-1 and SHA-256 are in there. There's like the Cha-Cha-20 generic blocks function is in there because developers realized that they're not going to use this crypto API stuff either. And maybe some maintainer will miss the fact that I'm just kind of putting this in the lib and then I can use it directly. And so this has happened a couple times, and there's now a bunch of stuff in there. There used to be half MD4 in there, which is some crazy algorithm used in like ext3 directory hashes or something. I moved that out of lib into ext3, but Anyway, there's a lot of stuff in there, and it's kind of haphazard. So Zinc is going to be kind of consolidating these into one kind of coherent, consistent place. On the implementation level, the current crypto API is kind of like a museum of ciphers. It has like, Cast5 and Serpent. God love it, but like who's using it? It just has all sorts of crazy things in there. MD4 and like the ripe MDs, and it's like it has everything, and it has tons of different versions of each of these implementations. And who wrote these? Are tons of different people over time? Are they any good? Are people actually using them? Actually reading them? Has this just kind of been sitting around? Have they been verified? Is anyone interested in crypto and good at looking at this stuff? Actually looking at the kernel's crypto? Do people care about this? It looks to me like a lot of that stuff has been sitting around for a long time. There's plenty of it that that is new, and there are people looking after, and there are new implementations. But there's also just kind of a lot of cruft in there. So for the implementations in Zinc, we're choosing order of preference. We're trying to get formally verified code if available. So I'll talk about that in a bit. If not, we're trying to get code that's kind of already in widespread usage and has gotten a lot of scrutiny already. Namely, for what we have now, this means anti-polycause implementations, which are pretty much the fastest for nearly all implementations, and are being used as well in OpenSSL. Say what you will about OpenSSL, but the actual primitives in them are quite nice, and they get tons of attention because crypto people and security people love to look at OpenSSL. If something is a little bit strange and we can't find anything that's actually being used, then the preference would probably be something that stems from the reference implementation as opposed to something strange or new or weird. So right now for Cha-Cha 20, we have the generic C, obviously, but we also have like all the different accelerated versions for x86, accelerated versions for ARM and ARM64, and a specific one for MIPS32R2. So this is for WireGuard mostly, so that you can take like a little cheap Linksys router and have fast packet encryption. Same situation for Poly1305, where we have the accelerated x86 situation, accelerated ARM, but we also have MIPS and MIPS64, which is nice. For Blake 2, we have accelerated x86. For Curve 25519, we have ARM acceleration, and we also have accelerated x86, but not using the SIMD stuff, not using the FPU registers at all. Rather only using these integer registers, but using these sweet new instruction sets that came in BMI2 and ADX that allow us to do nice things with carry and addition or carry and multiplication that makes big integer stuff in curves really fast without needing to do xsave and xrestore on the FPU registers. So all these are super high speed. I think for the most part, we're at the top of the benchmark charts for most cores and platforms. Okay, for the formally verified stuff, there are two projects I'm interested in for this. One is Fiat Crypto, which comes out of MIT, where they're developing these models of elliptic curves and other things too, but for the case I'm using for elliptic curves in a computer algebra system called Coq. It's a French software. And they're proving a bunch of different things about their implementation in Coq, like in this kind of pure logical mathematical reasoning place. And then they're somehow able to extract these representations from Coq into C. The C looks a little bit unidiomatic, but that's fine. That's something we can tolerate. It's still very readable, and we're pretty certain there's no errors. Likewise, and a little bit larger project is this Hackle Star. They're writing these descriptions in a language called F star. where they'll have like a description of what the primitive is and how it works, and then another description of what an implementation vaguely looks like. And then they can prove that these two things are equivalent to each other. And then they can lower the implementation description down into C, or in some cases down into assembly. And so this is a really cool project. It's out of INRIA here in Paris. So we've been working a lot with them to try and get their stuff into Zinc. The really nice thing about this is you have this C, it's pretty readable, normal code, and there shouldn't be any bugs in it. I mean, it'd be way less likely there'd be some vulnerability in this than in handwritten code that's handling all the carries and all the limbs and like complicated bit arithmetic. In this case, it's formally verifying that it's doing the right thing. Also, in the case of Hacklestar and Fiat Crypto for Curve 25519, the implementations they produce are the fastest generic C implementations available, which is pretty neat. I think the reason is they're able to remove certain superfluous things that are not obvious that you can remove them if you're trying to work the math out by hand, but because they have these provers, they can kind of experiment and debug and see what they can remove, and if it doesn't prove, then they don't do it, and so they can minimize it while it still proves, and so they have a lot more freedom to code things efficiently. So in general, I want this Zinc to have kind of stronger relations with academia. Or more broadly, the people who are actually designing these crypto primitives with real cryptographers. I'm not sure right now that there are many real academic cryptographers or like people actually making these primitives who care at all about the Linux kernel or really engage at all. It's kind of this weird esoteric place, hard to approach, kind of sequestered. So I'm trying to organize Zinc in a way that's appealing for the greater cryptography community, so we can actually have people who know what they're doing contribute and be excited about this. And smart professors can put scores of eager grad students to work on the kernel for us. And so I've already been talking to quite a few, and people are eager to find something good and important to work on. I think we should be seeing some attention in Zinc from that community. In addition to the formal verification for high assurance, everything's being fuzzed, which I think is kind of a must with crypto, with most code really, but with crypto it's just so easy to do that I consider this like a commit prerequisite. Something like LLVM fuzz, I mean, it's really easy. So this function, LLVM fuzzer test one input, gets called over and over with like varying quasi-random junk. And you get an input and a length of that input. And so I copy it to a bunch of different buffers. I call these three functions on those buffers, and then I crash if they didn't all produce the same result. And so this just runs over and over with like gradually mutating output, and it's got some instrumentation, so it tries to get through every different branch of the code if there are branches. Yeah.
How does the fuzzing look at branches if the crypto code is supposed to be constant time, so with as few branches as possible?
If there are no branches, it doesn't look at branches. If there are branches, it looks at branches.
Fuzz, how can you direct the fuzzing if there are no branches?
Indeed, it is the most important thing to have constant time algorithms. So that means in the math, you don't want to have, you don't want to be like branching on secret data or something. But there are lots of implementation details that do include implicit branches, like if you're reading in chunks of like 64 bytes or something, you have a buffer and then you chunk it up, and then like after the first 64 bytes, you go to the next, and you got to like add to the pointer, and then you go to the top of the loop again. But then what if like the last block is a little bit less than 64 bytes? like there's always these, little implementation details that aren't part of the crypto math, but are still part of the code. And it's important that all those different cases get tested. There are even interesting things like in Poly 1305, if the implementation is using integer arithmetic, the limbs are in base 2 to the 64 or 2 to the 32. But if we're using the vectorization, then it moves into base 2 to the 26 because it's more efficient with SIMD. So then what happens if we have a block that's called in vector mode, and so we move to base 2 to the 26, but then another one is later called in scalar mode because we don't have access to the FPU in kernel space, and now how do you reconcile this? So there are all these different ways these can be layered together that aren't in the crypto math, but are still important branches to test. Okay. Okay, so I mentioned this before, but we're trying to get things that have been used, that are well known, that are understood. This is also organized much differently than the current crypto API. We're organizing the code by the name of the cipher. So we have lib, Zinc, cha-cha-20, and then cha-cha-20.c is the C implementation. Cha-cha-20-arm.s as the ARM implementation, and so forth. So that way, if you're new to the code base or you're developing it and you want to find stuff, you look in the cha-cha-20 directory, and then you can see how cha-cha-20 is being used. You don't have to look in several different architecture directories and kind of follow the mouse around. This might seem like a totally trivial detail to put in a presentation, but in fact, I'm sure this will ruffle some feathers because it's different than what's currently going on. And I consider the ease of development that this gives to be considerable, not to have to chase things down. As a maintainer, it's certainly been helpful. It also has this cool thing where, because it's in the same directory, we can, instead of having different architecture implementations be called with function pointers and kind of things happening dynamically at runtime, we can use compiler inlining to do this for us. So we don't have any slowdowns with the rectoline stuff because we're following function pointers. We're always calling functions directly. So for example, for Poly 1305 emit, it's kind of like an internal function in Poly 1305.c. We first try and do it with an architecture implementation if it exists, and if not, we fall back to the generic one. Now, if there's not an architecture implementation, that emit arc is just an inline function that only returns false. So the compiler optimizes that if out and it's gone. So then we can write things in this kind of straightforward imperative way and have the compiler clean it up because things are in the same directory and they become part of the same file, then this is trivial to do. Likewise, we found that on basically every platform, the branch predictor is faster than function pointers with this stuff. So like here we have this Poly 1305 use neon. That's set when the module loads to see if the CPU supports neon. Not all CPUs will support it, and the kernel might be running on a bunch of different computers, like on a distro. And as it turns out, just a branching on that becomes super fast because that's in a read-only after init section. Right? It's never touched. It's always going to be the same thing, and the branch predictor does the perfect thing with that. It's like it's the easiest thing to predict. So really the only thing it winds up branching on is if this is true, which changes for important reasons, and otherwise falls back to the integer one. So we also do some things to make SIMD a lot faster. So traditionally in the kernel, the crypto looks like this. You call kernel FPU begin, and then you do some stuff that involves SIMD, and then at the end you call kernel FPU end. And before this, you're supposed to do a check where you see if you're allowed to use the FPU, because like you can't if you're in a hard IRQ on certain platforms and so forth. What kernel FPU begin does is essentially calls xsave. So it'll take all the FPU registers and store them in memory. And with things like AVX512, where you have like 5 12-bit registers and a bunch of them, that's a really expensive call. And then at the end, it calls xrestore. If you forget to do this, random programs in user space will crash when they try and use like an accelerated mem copy that's using those same registers. So it's like really a mandatory thing. If you find an instance where SIMD is used, but those aren't put in, it's a very fun and exploitable bug to exploit to try and get code execution in user space. Kind of a fun exercise. So anyway, traditional crypto code, you call begin and you call end and you do the SIMD stuff. The middle is very simple. But what happens then when you've got a bunch of packets and you're calling this in a loop? This means you're toggling the FPU on and off. You're calling xsave, xrestore, xsave, xrestore over and over and over. So it becomes really slow. So in fact, what we would want to do is hoist those begins and ends outside of the loop, but do so in a general way. So we have SIMD batching, where now there's a SIMD context. And you can get the context and you can put the context, which is a very similar paradigm to a bunch of other things in the kernel. Then you iterate through the packets, you encrypt it, passing it the SIMD context. Now, it turns out when you call kernel FPU begin and end, because it's calling xsave and it's holding those registers for that point in time, it means that you have to disable preemption, right? Because otherwise you can migrate to a different core and then you'd be dealing with the different registers and it wouldn't match up anymore. So you don't necessarily want to be running a long loop with preemption disabled that'll kill latency. So we have this SIMD relax that just sees if need rescheduled is true, and if so, just calls get and put simultaneously, or one after another rather. So when you use this in a loop, you add SIMD relax to the bottom, and then that ensures that latencies remain good. So then when crypto implementations actually use this, calling SIMD get won't actually call kernel FPU begin right away. It'll just set a flag that indicates whether or not it's available. Because what if when we call encrypt, we don't actually want to use SIMD in the first place, which is the case. For many ciphers, if the input length is too small, it's faster to use the scalar one and not to use SIMD. In which case, we wouldn't want to have the overhead of xsave and xrestore. So when you actually want to use it, you use SIMD use that both checks to see if it was available, and if it hasn't been set before, calls kernel FPU begin. So in this case, we go to the boring scalar code and never call kernel FPU begin if we don't actually need it. Okay, so that's it for the content. We can go into questions, but just to recap, it's definitely a change in direction and style of the current crypto API, but one I think is needed. It's a lot faster, it's lightweight, easier to use, probably gonna be fewer security vulnerabilities. It's being maintained by me and Samuel Nevis, who's a cryptographer behind Blake 2, Norx, MEMAAD. It's currently posted alongside WireGuard. It's in V6 right now. We're shooting for Linux 5. We'll see what happens. They're kind of like a lot of, people like to nitpick on the mailing list and kind of like filibuster these things indefinitely. So we'll see when we actually get it in, but we're shooting for Linux 5. Okay, any questions?
One, two. Does it work? Does it work? Hello? Yes, does work. So this is actually, it totally makes sense to have a synchronous API for a synchronous use case. obviously, I mean, the way you describe the crypto API, it's increasingly obvious that the whole thing was built around hardware accelerators, right?
Yeah.
I mean, you do not want to have a synchronous API for a synchronous piece of hardware.
Right.
And that's basically where the question comes in. Going forward, you probably don't want to be stuck with just only CPU processing. You also will want to have hardware offloads, I guess, for your accelerated packet encryption and decryption. Because if you especially look at the smaller microcontroller parts, so most of the ARM systems, all of these are gaining lots of hardware offloads for these. Even Intel CPUs do that these days, but you probably don't want to use that. Just because it's too far away from where you are. You're sitting too close to the data in your case. What's the plan to basically imagine we are in a world where Zinc is there, where everything is used as a synchronous API. How do we get that over to be asynchronous again as soon as we use accelerators, or do you have other plans?
So I can see a couple ways of approaching with this. One is to try and claim that like new crypto that people care about are getting synchronous instructions on CPUs, and so like out of CPU accelerators don't matter. I don't really know if that's true, and so not going to make that argument. Another way would be to evolve Zinc to handle some kind of asynchronous callback, but I think that might kind of pollute the API and complicate things. But rather, I would prefer in that department for either the current crypto API or a different API to evolve to some place where it can optionally handle asynchronous stuff, which would then wrap around Zinc for the software stuff or call out to some hardware device for other things. But it's the case that as long as there's software crypto around, you're going to need functions that supply those algorithms. And so right now these exist kind of like wired into the current complicated crypto API. But you could, what we're doing, we're taking that out and then they can just call into this. So I don't see any reason why an asynchronous API couldn't exist, but it's maybe an orthogonal goal to this, where we're just trying to get the actual algorithms down that do the synchronous part. It's also not clear that everything that uses crypto will need an asynchronous algorithm. So like, for example, that Bigkeys thing, like there it doesn't make any sense to call out some asynchronous device, whereas packet encryption or something certainly would, especially if like the crypto device is somehow linked up with the network card and so you can share buffers and all sorts of things like that. So in that case, then you're talking about wiring in asynchronous nature into how the driver works and handles the packet ingestion, which is fine, which is then grounds to use a different programming paradigm and thus a different API. Okay.
Hi. Earlier this year, you were at STIC, I think, also, and there was people from an area that were presenting another, I think it was Lib NSS, that is used.
Yeah, so this is Hackle, same thing, same project.
Yeah, so it's also using Hacklestar, and would that be possible to use both, or like a plugin, library, stuff like that? Can you mangle or merge the two code base?
I guess there's a little confusion where everything is. So Hacklestar is this cool project from INRIA where they're generating these primitives with formally verified C. Mozilla has taken Hacklestar and incorporated it into NSS to do OpenSSL. On the flip side, the Chrome team has taken Fiat Crypto, the similar project out of MIT. So NSS is using it in the same way that now Zinc is using it. So I don't know if we'd want to like plug NSS into Zinc or something, but like we both get the Hackle stuff. That makes sense.
The code that's already been done in the Lib NSS if it's possible to integrate it also in the kernel just for the implementation of the different.
I mean, that's what we're doing. I mean, we're both using the same code. It comes from the same place. The differences are basically stylistic, because the kernel has certain like function name styles and so forth, and so Hackle can generate code for different styles, or for like C89 versus C99, where variable declarations are. But yeah, we're both getting the same code, same implementations.
What I find interesting is that you managed to implement something which I would say boring, but in the positive sense, that beginners can take a look at when they want to understand some parts of the kernel. Because sometimes I have some questions from some people who ask me, what can I look at if I want to start with the kernel? And this question becomes increasingly difficult to respond to. And I think that having some low-level libraries which are pure C code that beginners can understand will help them figure where this code is used and progressively get an idea of how the kernel works. Because we have many layers of abstraction due to, for example, the asynchronous APIs or whatever, which makes this approach very difficult.
Right. I mean, on one hand, you wouldn't want a complete beginner to be writing like cryptographically sensitive code, but on the other hand, the implementations themselves are indeed like pure C. They take in data and they modify those buffers. And,
yes.
And so indeed, a beginner can probably understand what it's doing.
Absolutely.
Yeah, but then half of the crypto is written by people who are not programmers, right? They are mostly mathematicians, that sort of stuff.
I don't know about that. I mean, you do have these academic types who like can only do proofs and like are really smart, but like can't really code. But you also have tons of people in cryptography in particular who are just like killer coders, who know like everything about like microarchitectural details on like every core, and write like the most optimized assembly, and there are definitely some super talented people out there.
I think that, for example, a beginner would find it easy to replace one of these algorithms with a ROT 13 or XOR or something very simple, just to understand how it works.
Sure.
Yes.
There's a question back there. Oh.
Mm-hmm.
Question there, I think.
So I have a kind of a legal question. So there's code coming in from people who are not directly involved with kernel development, right? So how do you handle licensing? Do they understand like how GPL works and?
Yeah. So I'd say every academic I've worked with from that sphere knows plenty about GPL.
No, I mean they're fine with licensing this code.
But yeah, but in general, so we have things from a couple different places now. We have a decent amount of public domain code, which is then fine. The code from Andy Polikov and Cryptogams is dual licensed under BSD 3 clause or GPL 2. We have like an accelerator, the ADX stuff is like an LGPL thing, worked with Window on that. What else? The Blake 2 implementation is from Samuel. I mean, he, like was a co-author of Blake, the primitive, and naturally the implementations. I mean, we're not like taking code from terrible places. We're getting the permission we need, and I think in most of these cases, we're talking to or know the original authors. Mm-hmm.
So on this also I would add that, of course it's nice if you talk to the original author, but people already tell you whether they are good with you using their code by picking a license. So I mean, if they choose BSD, they are obviously good with you using it in any way you would like, sort of. If they pick GPLv3, they would not, and it's your responsibility not to use it. I mean, basically the license is how they tell you that that they agree or not.
So I've got a silly question on the naming. In the tradition of recursive acronyms, does the name come from Zinc is not a crypto API?
Yeah, so Zinc is not crypto slash, like the crypto subdirectory, but so I had that in the V1 and people kind of weren't so amused. So now, I don't know, Zinc is nice cryptography or. Yeah. But of course. I mean, also now there's lib sodium and lib chloride and so forth. And so now we're Zinc, kind of continuing the tradition of these types of names. Looks like I have 2 minutes left, so maybe that's one more question if there is one. Okay, thanks a lot.